Why is it called this way? I don't really know why this is the most popular way of addressing this theorem. Obviously, there's many ways of talking about this, but the idea is that I will help you solve problem 6, question 1, part C, and the same trick actually works to solve any other part of question 1. But 1C is trickier, and let me tell you why. So the problem. Here is the problem. Let's say you don't know anything about combinatorics and you're trying to solve question 1. So the first question is, how many strictly increasing functions are there from a set of size n to a set of size m? Let us solve 1b first, because in this context it might be a bit easier. So 1b says, how many injective functions? How many injective functions? Now maybe you already know this because this isn't too hard to figure out. And here's like the most low level way of solving this. It's not the only way, and it's not the best or shortest way. But this is, like I said, if you don't know anything about combinatorics, this is one way you might try to solve this. How many injective functions? From what is it? N to M, I think. Yeah, from N to M, right? So if you think about it, we can use the following notation, and feel free to use this notation as well. It is kind of informal, but I think in this context, it makes it actually clearer. So we can write all of these functions are finite, right? They have a finite domain and even a finite codomain. We can just write them like this. So f0, f1, f2, f3, and so on until the last element of the domain, which is, of course, n minus 1. Is it the same as the one above? I hope it is. Yes, it is. Okay. So this is like a short sequence, right? And essentially this is a tuple with n minus 1 elements, and each coordinate is either 0 or 1 or 2 all the way up to m minus 1, right? So using this notation, it is actually not too hard to figure out how many injective functions there are. You can use the box method, right? What are our possible, maybe I should write it like this, what are the possible choices for the first element that the function takes, the first coordinate? Well, this is easy. I can take any element out of the m minus 1, sorry, actually it's m. Out of all the m options, well, I could pick any of those. Once I pick the first one, then for the second one, I can pick any element except the one I already picked because it's injective, so there mustn't be any repeated elements. And for the next one, I have m minus 2, and so on. And the last one, if I already picked everything before that, is determined, right? I can only pick whatever is left over. Is actually, that's not true because n could be smaller. Okay, let me fix that actually. So this should be whatever is left over, which, unless I made a mistake, should be n minus m plus 1, right? Let me think about this for a second. Yeah, that works. Okay, so the answer, there we go. The answer is m times m minus 1 all the way to whatever is left over, right? So these are the only options. And if you want to write this succinctly, you could just say this is m factorial divided by n minus m factorial, if you notice that. And this is no coincidence, but it is actually n factorial times the combinations of m and n. And you can think about why that is true, or what this equal sign means beyond the algebra. Okay, a similar idea works to solve 1a, because for 1a, it is basically the same thing. You're not allowed to repeat elements. But once you pick a sequence of different elements, there is only one way to sort it, namely in increasing order, because 1a is asking how many increasing functions are there, right? So all you have to do is take this number and divide it by n factorial, which is all the ways of rearranging this n tuple. So if you know how to do 1b, then you know how to do 1a. But here's where it gets problematic. So the problem is, what if you're trying to do 1C? And this is why I want to talk about this separately and even spoil the solution for you. So the problem with 1C is that this very naive trick doesn't work anymore. And let me tell you why. Now we want increasing functions. Some people call this non-decreasing, but for me, increasing and weakly increasing is the same, right? This is all clarified in the problem set in case you haven't looked at it. Now we want increasing functions. Now, what is the problem with this? Again, I want to find a sequence f1, sorry, f0, 1, 2. And now the condition is that whatever I pick has to be less than or equal to the thing before it, right? Okay, so let's try to use a similar trick and you'll see why this doesn't work at all. So what are the options for the first element? Well, now we can repeat elements, but the order is the thing that matters. So can we pick any element for f0? Well, kind of, right? And the problem is that we are actually more restricted in what we can select. For example, if f0 happens to be the largest element, namely n minus 1, then let's just say, for as an example, that this value happens to be n minus 1. It could be, right? But if I choose this to be n minus 1, then all the other elements are determined because they have to be at least n minus 1. And the biggest they could be is n minus 1, since that is the, wait, sorry, I think I messed this up. M minus 1, right? This is the domain, and the other one is the codomain. So if I pick m minus 1 as the value of f0, then all the other ones need to be m minus 1 as well. So this will complicate the counting because it means that whatever choices I have left depends on whatever choices I made before. And this seems like there will be a lot of cases, or it will be super messy to use the same argument. How many options do I have for the first one? I mean, technically I could pick any element, right? There's no restriction. But depending on what I picked, the second element will have either all options. For example, if the first element I picked is 0, then the second element can be whatever. It just has to be at least 0, but of course it will be. So I still have m options, including 0 itself. So will this be m, or will this be 1, or anything in between? So it feels like this method of counting using the boxes doesn't work here at all because the choices are too interdependent, right? So clearly, we're not thinking about this the correct way. And like I said, you would probably use a method like this if you don't know anything about combinatorics. But we do know combinatorics, so there's a better way of doing this. And I am about to tell you what it is. So I will tell you what the theorem is, and then I will tell you how to connect those two ideas, right? So the theorem says the following. And again, this is one of those things that it's better explaining this in an informal way. If you want to write this with functions and sets, that is also fine. That is my preferred method. But I think in this case, you will understand this and actually assimilate how to use this and commit it to memory if I give you the intuitive explanation. So the reason this is called the stars and bars theorem is because one way to picture this is using stars and bars. So what is that? Okay, so the idea is the following. Let me maybe reorganize this a little bit. Stars and bars. Okay, so this is the discussion about problem 6.1c. And I think some people on Piazza asked if they could use this, so this is obviously familiar to some of you, and yes, you can use this. So there's a better way. Okay, so here's the easiest explanation that I can come up with of the stars and bar theorem. So we have a bins and n objects. Now, the objects are indistinguishable in the sense that swapping out two objects makes no difference. I have no way of distinguishing the objects, so they are not enumerated, right? These objects don't have labels, they don't have numbers. Indistinguishable. Indistinguishable objects. And I want to put the objects into those bins. Now, right now, I don't care if the bins are empty, but that is a variation of this problem that could help you solve part 1a of the problem set. And it's a variation that's actually simpler than the thing I'm about to do. But there's no need because you can use the previous argument to solve the other ones. So let's do the hard one or the slightly more difficult one, right? So we want to place the objects, or rather, in how many ways? That is the question, right? In how many ways can we place the objects in the bins? Now, the objects are not distinguishable, so if you have two bins and you swap out the objects, as long as it's the same number, we don't care. We consider that the same situation. But the bins are distinguishable. So let me tell you what I mean. Let's denote the objects with stars. And like I said, we can't distinguish them, so I will not give them individual labels because the order doesn't matter, just the amount, right? So these are the objects. And here are the bins. So there's bin number 1, and that one is different from bin number 2 and bin number 3, all the way to bin number, maybe for consistency, I should label these starting with 0, enumerate them. Anyway, it doesn't really matter. And the question is, how many ways can we distribute the stars in these bins? For example, I could put all stars in the first bin and leave all the ones empty, right? So bins can be empty, can be left empty. I could put one in one, trying to get all bins to be non-empty if I really wanted to. And I could do that. So how do we count this? This isn't different from counting tuples or things we've already done, but thinking about this in this way is useful. So here's the trick. And once you learn this trick, you will always think about this trick. I'm going to put bars in between the bins to separate them. And here is the big insight. And this is the insight that should also tell you how to solve 1C. The insight is when you have something that is difficult to count because it depends on many things, then maybe you're focusing on the wrong thing. We don't have to focus on the sequence or the numbers. We focus on the things in between the numbers, in between the sequences, right? Like here, we are not focused on the objects, we are focused on the bins. So basically, any configuration of stars put into the bins will look like a sequence of bars and stars. How many bars do I have? I should have, let me think about this, k plus 1, right? If there's k bins, and I have, how many did I say I have? Okay, so that's n objects, that's k, right? Now we could maybe, just to be consistent with other sources, let's not put bars in the at the end, right? So let's make it k minus 1. It doesn't matter, of course, it's the same idea. But yeah, let's suppose that the first bin doesn't have a wall, right? It starts before the first bar, and so on. So it doesn't matter at all. It's the exact same thing. So how do we figure this out? Any configuration is a sequence of bars and stars, right? It's something like this. So this one is saying the first bin has 1 star, the second one has 2, then there's an empty bin, then there's maybe 3 stars, and then there's another empty bin, which is the last bin, right? We agree that the first and last bins only have 1 bar on each side. Sorry, 1 bar on one side. Okay, are there any questions so far, or does this make sense? I think this is pretty clear, right? One way we could do this is we could just count all the possible permutations of these symbols and then eliminate all the ways we overcounted, right? So there are, how many symbols do we have in total, by the way? We have n stars, right? And we also have k minus 1 bars. So that's the total number of symbols. This number factorial gives me all permutations of this sequence, but I'm overcounting because the stars are indistinguishable, right? If I swap out this star with this other star, it's the same configuration, even though this factorial is counting them as separate. So how do I account for that? Well, just eliminate all the ways of permuting the stars, because for every permutation of stars, you're counting one too many. And the same happens for the bars, right? The bins are distinguishable because the order matters, but not the bars themselves. I could swap out these 2 bars, and it's obviously the same bins and it's the same configuration, right? So I have to eliminate the k minus 1 factorial for the bars. And this is such configurations. Now there is a different way of thinking about this, and unless I made a mistake, these 2 numbers should match. How do you say this? Alternatively, if you think about this, this is a binary situation, right? I am picking out a sequence, and in each box, I'm allowed to make a choice of either 0 or 1, star or bar. This is awfully familiar to a characteristic function, or if you will, a subset. Think of stars as elements in a subset, right? So how many elements does the set have? Well, it's how many boxes we have, right? And the total number is n plus k minus 1. And we are picking the number of stars. So this is just n. Now, why stars and not bars? Well, if you want, you could just pick the number of bars instead. So unless I made a mistake, and you can tell me now if this makes sense, maybe there's something that I need to clarify. Unless I made a mistake, all of these numbers should match. Wait, do they even match? How many do I have? N and k minus 1. Okay. Four bars. So here's a question for you, and if the answer to this question is yes, then we all understood, and then we can move on. So the question is, do these all numbers match? And if they match, that is the answer, right? That is the answer to the question, in how many ways can I put stars in bins? The answer is, well, whatever this calculation is. And I will tell you why this is useful in a second. So please, if you can, answer the question. In the meantime, I'll tell you, how do we apply this? To question, what was it? 1C. And here is the trick. It's a proof by sketch. Of course, you have to write something down during the problem set, but an informal argument is okay as long as you do include the details. This is one of those things that's annoying to write down formally, but it's also good practice. So this is an increasing function, right? You're allowed to repeat, but you're not allowed to go down. You can stay on the same level, you cannot go down, right? So this is domain and the codomain, right? So this is 0, 1, 2, and so on. Okay, so you can start with 3 zeros, then you can have this number of ones, and then this one. So how do we make sense of this? We're trying to count how many functions f there are that have this property. And here is where the stars and bars come into play. I'm going to put a bar in each of these levels. Levels could be empty, right? I could skip the level number too. In fact, let's do that so that you see that I am allowed to skip levels. It's not a surjective function, right? Surjective would be the bins need to be non-empty, but that's not what I'm saying, right? So you could have something non-surjective, right? No one's covering the number 2. That is perfectly fine. And what are the stars? Well, the stars are just the number of elements you have. So for example, here we have 3 elements, so that's 3 stars. There's 2 elements here, so that's 2 stars. 0 stars, then again 2 stars, 1 star, right? And if you think about it, that is exactly the same thing. So your task is use this idea. This idea, and by this idea I mean what I just explained, to show that there are n plus, actually I think it should be m, because in the question c is written in terms of m, not of k. Same thing, right? Such functions. So you have to prove that there is a bijection between the stars and bars and the increasing functions. And you can do the same thing. Similarly, if you find this a bit confusing, there's an exercise that you can work on, which is today's quiz. You can prove using the exact same idea that there are n plus m minus 1 solutions, integer solutions, of course, to the following. You have m numbers that adding up make n, but you want each number to be non-negative. In how many ways can you do that? In how many ways can you partition the integer n into m pieces such that each is non-negative? Of course, if you allow negative numbers, then there's always infinitely many solutions, because you can always just take 1 plus minus 1, 2 plus minus 2, and do this as much as you want. So of course there's infinitely many solutions without this restriction. You can also ask yourself, what if all numbers need to be positive? You can reduce one to the other, but I think we've talked enough about this. Okay, so I'm getting some questions in the chat. Let's see. Okay, so let's explain the theorem a little bit more. Did I even write down the theorem? Okay, I didn't write this as a theorem, but it's better. So the theorem says the following. We're trying to put stars into bins, and the question is, in how many ways can I do that? And yes, you can directly apply the formula in the quiz. Yes, but you do need to justify why that number is the same as the number of solutions. Again, finding a bijection, you don't have to write a formal bijection, but just say, for every solution, there is something like this, you know? For every solution, there is a star and bar situation. So, sorry, getting back to the stars and bars, the question is, how many configurations can I find of stars and bars? And the trick is to realize that every configuration of stars and bars is just a sequence of length n plus k minus 1, because there are n stars and k minus 1 bars. There's k bins, right? So I only need k minus 1 bars to divide, to separate those bins. Now, that number by itself is not enough because it's overcounting, right? For every one of these configurations, if I move around the stars, it's not changing the configuration, but it is a different permutation. So I have to divide out by n factorial to get the correct number. And I also have to divide, for the same reason, by k minus 1 factorial to get the same number. That is just one way of thinking about it. Another way to think about it, and maybe I can add a few more details here. Imagine that you have a set and you're picking out which elements will be in the subset and which ones will not. That is exactly what this symbol is defined to count. It's counting how many subsets there are of a given size, right? So let's say that this one will be a star. This one will not. So I'm thinking it will be a bar, but I don't have to write that down. Maybe this one will also be a bar, and this one will be a star. And this one will also be a star. This one will be a bar, which I can just leave blank. And how many ways can I do this? Well, this is just a subset that contains this one, that contains all of the stars and does not contain all of the bars, right? So this symbol is saying, in how many ways can I choose n out of a set of size n plus k minus 1, right? We literally read this as n plus k minus 1, choose n. So these are all different approaches to solving the same problem. And like I said, all of these numbers, which are different ways of explaining the same thing, should be the same number. Otherwise, I made a mistake. But no one has complained so far, so I think this makes sense. Okay, and there's another question. Isn't this the same idea as ordering the bins, allowing repetition and considering order? Yes, of course, of course. It's the same, it's the exact same idea, yes. Um, but you're allowing repetition inside the bins, right? The bins themselves are different, are distinguishable. So there's many ways of thinking about this. And like I said, I'm not sure what this is called, the stars and bars theorem. Maybe someone thought this was the easiest way of explaining this idea and they just came up with stars and bars. You can come up with any sort of symbols that you want, right? I think stars and bars is nice. It's easy to connect this to other ideas. And so the trick is, how do you count the number of increasing functions? Well, don't focus on the values of the function. Focus on the gaps in between. Focus on the jumps, because those you can count. Those are just bins, right? And each bin tells you how many elements there are of a given type, right? So for example, the first bin tells you how many zeros. This is the bin of zeros. It tells you how many zeros there are. And those zeros can only be in one place. They have to be at the beginning of the function. And the second bin tells you how many ones there are. And these ones can only be in one place, which is after all the zeros. So the bins are ordered because the function is increasing. There's no other way to put this, right? In other words, if you have a bars and stars configuration, you can produce an increasing function. And conversely, if you have an increasing function, I just told you how to get the bars and stars. It's this drawing. Now you do have to write it down maybe a bit more formally than that to be acceptable, but you don't have to explicitly define a bijection and prove it, as long as the idea is clear. This idea is very powerful. Stars and bars show up in many other places, and we could have even done everything just in terms of stars and bars, right? The symbol of choose itself, the combinations, something just with stars and bars. Okay, so we have we have 10 minutes left. So I will stop the recording here and take your time to finish the quiz, which is how to use this idea. The same idea can be applied to problem set 6, question 1, part C. I will be here should you have any questions, and after that we will move on to something that is also important for the exam, the final exam. Some more examples, and hopefully in the last half hour we can talk about something else, another application. Okay, so let me stop recording.